So it's actually 6.1 Laplace transform. It's a definition. Laplace transform. Okay? Let me give you the definition. The function of S is the cursive L of a function in time domain from 0 to infinity e to the minus st times f of t dt. That's the definition. That's the definition of Laplace transform. Okay? Do you get anything? This big F is some variable in S domain, I told you, right? So it's like Y, right? Big Y. S is a variable, independent variable in S domain, right? And L is Laplace operator, okay? F is any function, right, in time domain. Big F is any function in S domain, okay? Equal the integration of from 0 to infinity, okay? E to the S minus st times the any function in time domain, right? dt. Term by term, okay? This is a function in S domain, okay? This is Laplace operator. This is function in time domain, right? T domain. And this is just integration, right? Integral from 0 to infinity. And we need to, figure out why. Why 0 to infinity, right? It could be minus infinity to infinity, or minus infinity to 0, 0 to infinity, right? Y from 0 to infinity, okay? And this, e to the minus st, very strange looking function, right? It's actually called kernel. Kernel between S and T domain. Wow, what's that? Kernel, it has another meaning, but you can think of it as a bridge. Right? It's a bridge. It's a bridge between T word and S word. Okay? Very philosophical, right? Isn't it? So I'm going to give you some basic calculation of Laplace transforms. Okay? So, for example, example 1. The function is 1. Okay? The most basic number or function, right? Which is 1. And let's, take an example for that. And time is greater than 0. I mean, because this is a time domain. This t is time, so it's greater than 0, right? All right. So let's put f into Laplace bus. Okay? Then that's 1, right? And from the definition, from 0 to infinity, e to the minus st times 1 times dt. Okay? That's the definition. And definitely we can do this calculation. So improper integral, okay? This is improper integral. We can't do this integration as a normal way. We need a special way of limiting. Okay? T goes to infinity. So 0 from to t, right? We need definite integral. So kind of rewriting this form. That's the improper integral, right? Okay, so it's like, it's like integrating under the curve infinitely, going. Okay? So we need limit process. All right. So if you do that, it's limit t goes to infinity and minus 1 over s e to the minus st from 0 to t. Okay? And so this is limit t goes to infinity. So minus 1 over s e to the minus st, so plus 1 over s e to the 0. Okay? So t goes to infinity means 0, right? So it's a e to the 0 is 1, so it's a 1 over s. Okay? So it's a fairly easy calculation that L Laplace transform of 1, the function 1 or number 1, is 1 over s in S domain. In usual sense, we don't actually do this. We just from here and to here, okay? Limit, once you know it's an improper integral, I mean, next time you don't have to, write all this stuff, okay? So it's okay to write from there to there. Example 2. The function is e to the at, where a is just a constant number, okay? Any real number, right? So again, so Laplace of e to the at is from 0 to infinity, e to the minus st times e to the at, dt, right? And that's from 0 to infinity, e to the a minus st dt. Okay? And so you do this integration. 1 over a minus s e to the minus s minus a t from 0 to infinity. Okay? And then that's 1 over s minus a. Okay? So Laplace transform of e to the at is 1 over s minus a. Linearity of Laplace transform. Okay? This is really important. Okay? So I'm going to explain linearity of Laplace transform. Mathematically, this is it. F of t plus b g of t. Okay? So we have a linear combination of functions. Okay? And we are taking Laplace bus for the whole function. Okay? And then this is a times Laplace of f plus b times Laplace of g. Taking bus all together is like taking bus each. Okay? And then add them later. So that's the linearity. That's exactly what linearity is. Mathematical proof, which is really easy. Okay? So a, f plus b, g, and you put it into the definition, right? So e to the minus st, af plus bg dt, which is a times 0 to infinity to the minus st times the f dt plus b times 0 to infinity e to the minus st g dt. Right? Fairly easy. A L of f plus b L of g. Okay? In S domain notation, A big F, right? Plus b big G. You can write that way too. Next, cosine sine. Okay? Next, the basic or fundamental functions are cosine and sine. And the derivation of cosine sine is kind of tricky. Right? So Laplace of cosine omega t is from 0 to infinity e to the minus st cosine omega t dt. Okay? And this is e to the minus st over s minus s cosine omega t from 0 to infinity minus, this is integration by parts, okay? omega over s, 0 to infinity, e to the minus st, sine omega t dt. Okay, and wow, this one becomes 1 over s minus omega over s sine of, Laplace of sine. Laplace of sine omega t. The calculation gives, the calculation of cosine gives in terms of sine. So it's referring each other, sine and cosine. Okay? And let's calculate sine this time. Sine omega t. Okay? From 0 to infinity, e to the minus st, sine omega t dt. Do the same thing. Eventually, it'll give you omega over s, Laplace of cosine omega t. Okay? And so this is a two equations, right? Relates to each other. So you can plus minus and then you can solve it. Eventually, Laplace of cosine omega t is s over s square plus omega square. Laplace of sine omega t is omega over s square plus omega square. Okay? I'm kind of skipping, the calculations, but you can, you can do it yourself. All right, let's solve it together. So Laplace transform of t, function t, is from 0 to infinity, e to the minus st times t dt. Right? So you need to do integration by parts, right? So this is, let's say this is u, this is v prime. Okay, and if you do that, so this is minus 1 over s times t e to the minus st, uv, okay, from 0 to infinity. From 0 to infinity, this is minus 1 over s e to the minus st dt. Okay, so it's a u prime v. So this is actually, so to the infinity, so it's a 0, right? And minus 0 is a 0. The first term is 0. So it's a plus 1 over s. You have to integrate it. That's this, right? Okay. So see, t is 1 over s square. Cosine and sine is this. E to the at is 1 over s minus a. 1 is 1 over s. There's no really relationship in the time domain and s domain. They're totally different. Their figure, their shape, their relationship is totally different. So you have to be familiarize yourself to these finer forms. Okay. All right. And one last function. 자, 마지막으로 하나 더 할 텐데, 이게 책에 있는 증명하고 좀 달라요. 책에 조금 헷갈리게 써 있어. 오케이? 그래서 이거 잘 들으세요. Okay, so Laplace transform of t to the a. Okay? So a is a real number. Okay? So this is from 0 to infinity, e to the minus st times t to the a dt, right? And you need integration by parts. That's hard, right? You have to do first substitution. X is st. Okay, we have intermediate variable x. That's st. So, which is dx is s dt, right? S is constant in time domain integration, right? All right. So Laplace of t to the a becomes from 0 to infinity, e to the minus st is minus x, right? And t is x over s, right? T is x over s to the a, and dt is dx over s. Okay? So by the substitution, that integration becomes this way. Right? Then, if you do that, that integration, actually it will be 1 over s to the a plus 1, right? Because there's a s down there, right? And this is from 0 to infinity, e to the minus x times x to the a dx. Okay? This is exactly gamma function. The definition of gamma function is this. Gamma of a will be from 0 to infinity, e to the minus x times x to the a minus 1 times dx. Okay, that's the definition. Laplace of ta is gamma a plus 1 over s to the a plus 1. That's fine, okay? But we got a trouble. I mean, gamma itself, its definition-wise is hard, right? To calculate, right? So we need simpler case for this. Because, it's hard to handle this gamma function, right? But if you say t to the n, what is n? N is integer. Okay? The generalization of a is real number, 1.5 minus 100.707, right? The general value is this, but if we constrain to integer, 1, 2, 3, 4, right? Then it will become much easier form. Okay? Let me show you. So for a, which is greater than 1, the gamma becomes a times gamma of a. Okay? From the definition. This one, you can easily draw this conclusion, okay? That property. If you need some proof, then that's from 0 to infinity, e to the minus x to the a dx. Okay? And integration by parts, u v prime, and the uv is x to the e to the minus x from 0 to infinity minus from 0 to infinity, u prime v, a minus 1 times minus e to the minus x dx. Sorry for here, right? But then that's a times from 0 to infinity e to the minus x times x to the a minus 1 dx, which is gamma of a. Okay? So this is just definition, calculation based on definition, okay? That's the property, very important property. But then still, there's a gamma, all gamma there, right? We cannot, easily handle that gamma function, right? So let's assume integer numbers. Okay? N is 1, 2, 3. Then it's n factorial. Do you get it? Here, a times the gamma of itself, meaning if it is an integer, okay, then it becomes factorial. All right? Then we get rid of gamma here. Then L of t to the n instead of t to the a, t to the power of integer numbers becomes n factorial over s to the n plus 1. Okay? So we get rid of gamma out of the equation. 테이블을 다시 보면 자, 왼쪽이 function in time, 그렇죠? 오른쪽 열이 그거에 대응하는 S 도메인 펑션이 되는 거죠, 그렇죠? 그래서 라플라스를 태워라, cursive L이다. 그러면 왼쪽에서 찾아서, 그렇지? 오른쪽에 대응되는 거를, 그렇죠, 여기, 그렇죠? 찾아서 오른쪽에 대응되는 걸 쓰면 되는 거고, 만약에 다시 S로 이루어진 펑션들을 주어주고는 T를 구해라. 그러면 그거에 해당하는 T를 구하면 되는 거예요. 이게 테이블을 보는 방법은. So another important property to handle Laplace transform efficiently is S shifting. What is SS? You know that, right? This is an independent variable in frequency domain, right? And shifting, what's shift? Shifting is actually this. Let's say this is a function, okay? And shifting, after you shift, it becomes, that's shifting. So you're moving entire, function or curve, okay, in time dependent, way. So like A, right? So it's like T minus A becomes, right? T equal. Okay, that's what's happening when you shift a function in time domain, right? Let's take a look at the same situation in S domain, okay? What is S domain curve? Usually this, right? Let's say, just for an example, all right? And you shift in S domain, which is actually S minus A, something like that, right? But then this one becomes this, that, okay? So like A to the amount of A. A is frequency here. A here is time T, second, right? That's the shifting in both domain, okay? And what is this? S shifting, meaning this one. Shifting in S domain. That's what S shifting is, okay? Then, naturally, T shifting is what? This. Okay? Alright, so S shifting and T shifting, you clearly understand, what's going to happen for that shifting, right? So let's talk about the S shifting in mathematical way. Okay, have that in mind. Formal definition of S shifting is this. Okay? So any function in S domain which is shifted by the amount of A is in this case a frequency, right? It should be some frequency. It's shifted. The entire thing is shifted like this, right? Then that's the same as multiplying function e to the at in time domain. That's the multiplication of e to the at when you shift something in frequency domain. That means in time domain it's a multiplication of e to the at. Wow, this is really important. Okay, you have to understand that. You have to understand this mathematical form plus this what's happening. Okay. That really has to be in your brain. Okay, so let's prove this mathematical stuff. Is this really true? All right. So f of s minus a is from the definition. So if you need proof, if you need something, you have to go to the definition. Okay, then you'll know everything. So from 0 to infinity, e to the minus s minus a T f dt. right? So it's 0 to infinity e to the minus st, okay, times e to the at f dt, which is Laplace of e to the at times f. Okay? So proof is rather simple, but you have to fully understand the underlying concept and visualization. Okay, let's take an example. So f of t is e to the minus 2t sine t plus 3. Laplace of f is, so you have to use the linearity, right? Because it's composed of many basic functions, right? So you need to use linearity plus you have to use time shift. Okay? So whenever you see a function in time domain, look at exponential first. Okay? See if it's shifting or not. And linear combination. Then you're using both linearity of Laplace transform and S shifting for this problem. Okay? That's what you do. All right. So Laplace of, you first take all the function in the bus, and probably you can, yeah, and linearity. So e to the minus 2t sine t. You cannot separate these two because it's multiplication, so you cannot do that separation. But you can do this, right? Okay? So that, then, so if you have an exponential multiplication, all you have to do is find the corresponding function in S domain, which is sine t is what? Omega over S squared plus omega. And omega is in this case 1, right? So it's a 1 over S squared plus 1. Okay? That's a usual, normal, sine t. But in this case, it is multiplied by the exponential, right? That means in S domain, it's S shifting. So this S is not that S, but it's e to the minus 2t times sine t is 1 over S is S minus A. Okay? And A is what? Minus 2. So it's a plus 2 square plus 1. Okay? All right? So this one becomes 1 over S plus 2 square plus 1 plus 3. The primitive form is 1, right? 1 times 3. So it's 1 is 1 over S, right? So it's 3 over S. And you do this, calculation. So at the end, it's S square plus 4S plus 5, 3S square plus 13S plus 15. Okay? In S domain. That's how you do.